Let's talk about finding limits using a process called L'Hopital's rule. L'Hopital is spelled this way a lot of times. Sometimes people spell it L'Hopital's rule, but it's a French word named after a guy named L'Hopital, of course. That's what math does. So, what we're going to do is we are going to find limits. So, L'Hopital's rule to find limits. Now, some of these limits that we're going to find are ones that you can find other ways, and some of them are pretty difficult. So, let me give you the preface of this. In order to use L'Hopital's rule, you must, absolutely must, have an indeterminate form. Now, what does that mean? Well, let me see if I can spell that correctly. Indeterminate form, that means that you've got to end up with something that looks like infinity over infinity, 0 over 0, or something of that nature. Now, sometimes when we have things like infinity to the 0, we can work that because we can work with logarithms. And so there are a lot of options, but these are primary indeterminate forms. If you do not have indeterminate forms and you use L'Hopital's rule, it will not work. Most of the time it'll give you the wrong answer, so that is not good. All right, so let's look at an example of something that you have probably got an answer for already. Now, this is going to use L'Hopital's rule. Here is L'Hopital's rule. First of all, if you've got this in a fraction form, then L'Hopital's rule says, says basically here that the limit as x approaches c, or whatever, of some function f of x over g of x, okay, with indeterminate forms, is equal to the limit as x approaches c of f prime of x over g prime of x. Now, that is not the quotient rule, and it does not take the derivative of the quotient, but it does work for this process. So if you want to try that, that's what we're going to do. In fact, I could keep taking derivatives over and over and over again if I have indeterminate forms. So let's look at an example. Back early in Calc 1, you found the limit as x approached 0. So here's an example. As x approaches 0 of sine x over x. And you probably use the squeeze theorem to figure out that the answer to that is 1. Now, let's use L'Hopital's rule, because if you put x equals 0 in here, you get sine 0, which is 0 over 0. So that would have been 0 over 0. So let's use this rule. That's the limit as x approaches 0 of the derivative of sine, which is cosine x over 1. Now, cosine of 0 equals 1 over 1 is 1. So there's your answer. So that's pretty slick. Now let's try this with some things that are maybe a little bit more challenging. So here's another example. I'm going to take the limit as x goes to infinity of x over the square root of x squared plus 1. That one, normally you would divide by x or the square root of x squared. So you could do that, but as you go to infinity, this one goes off to infinity, as does that one. So we're going to use L'Hopital's rule, and we can do that by taking this as 1. This one is 1/2 times x squared plus 1 to the minus 1/2 times 2x. I can cancel the 2's. I can kind of swap this stuff around and take a look at this. This becomes the same thing as the limit as x approaches infinity of the square root of x squared plus 1 over x. Look at that. Isn't that weird? It just flops over. Well, I can tell right away that I'm going to get nowhere on this thing. So I cannot use L'Hopital's rule just because the process doesn't work on this one. So what we would normally do, and this is kind of old stuff, it's not L'Hopital's rule, but as x approaches infinity, you would divide by the square root of x squared, which in this going to infinity is equal to x. So I'm going to divide each part. So this is not using L'Hopital's rule, but it's what we need to do. That's an x squared, and then x over x, that's the equivalent. So we would end up with the limit as x approaches infinity of the square root of, doing this, 1 plus 1 over x squared, and this is over 1. So we would have the limit as x approaches infinity of this, 1 plus 1 over x squared. As x goes to infinity, 1 over x squared goes to 0. So we would end up with the square root of 1 or 1. So that one did not really work well with L'Hopital's rule. Now let's look at another one that would work well. This one is the limit, so here's another example, as x approaches 1 of the ln of x over the sine of pi x. So as x approaches 1, I get ln 1, and sine of pi times 1 is 0. So sine of pi is 0. So we're going to have 0 over 0. So this one fits for L'Hopital's rule. So we can take the limit as x goes to 1 of the derivative of ln x, which is 1 over x. The derivative of sine pi x is cosine pi x, but pi x is not a simple angle, so we have to take its derivative, the chain rule, so we multiply by pi, and then we plug numbers in. So here we plug numbers in, we get 1 over 1, so this is 1. Cosine of pi, 1 pi is negative 1, and this is pi. So we end up with minus 1 over pi. So L'Hopital's rule worked really well there. Now let's try another one. This one is kind of interesting. It is an indeterminate form, but not in the normal way to write it. So this is the limit. Whoops, I started to do that. X approaches 0 from the plus side, and we'll take 1 plus 1 over x to the x power. Now, if you plug 0 in, you would get 1 plus 1 over 0 is some form of infinity, okay, raised to the 0 power. So this is bad notation if we write it this way, but 1 plus infinity to the 0. In other words, infinity to the 0. That is indeterminate, but not as a fraction. So consider this. We've got to consider the fact that y equals 1 plus 1 over x to the x, and then we've got to rewrite this. I need to use the idea of taking the log of both sides. So the log of y, and the log of this is x times the log of 1 plus 1 over x. So this one is a little bit better because it's not raised to a power. And I'll just find the limit of this one and then I'll come back, all right? So this one is, if I let x go to 0, I'm going to have 0 times the log of infinity. That's not exactly indeterminate either, but we've got some options. We can say that this is the ln of 1 plus 1 over x, and then we're going to move this x down here, so we create a fraction. Now the way to do that is you call it 1 over x, all right? So reciprocal and work it that way. So now, if we put x is 0 in, we'd have ln of infinity over infinity. So that's an indeterminate form, because ln of infinity is infinity, and 1 over 0 from the plus side is infinity. So we've got to do this work first. Now, let's find the limit as x approaches 0 from the plus of this, the ln of 1 plus 1 over x over 1 over x. Using L'Hopital's rule, I can take the derivative of ln, which is 1 over. So let me move down just a bit here. So I'm going to have 1 over 1 plus 1 over x for that piece. Now the derivative of 1 plus 1 over x is minus 1 over x squared. That's the derivative of 1 over x. Then I divide by the derivative of the denominator, which is minus 1 over x squared. So these two guys cancel. And so now we've got the limit as x goes to 0 from the plus of 1 over 1 plus 1 over x. 1 over 1 plus 1 over x, which is kind of a mess. So I'm going to multiply by x over x. That gives me this. I've got the limit as x approaches 0 from the plus. I've got x on top. Down here, multiply this. I've got x plus 1. Now, as we go to 0, this is not indeterminate. This is actually a value, isn't it? So as x goes to 0, this goes to 0. Because we're going to have 0 over 1. So 0 over 1 is defined, and it's equal to 0. All right, now we've got to go back and actually answer our question. So we found that the ln of y is equal to 0. So the ln of y equals 0. That means e to the 0 equals y. So e to the 0 is 1, so 1 is equal to y. So our limit here is going to be 1. So 1 plus infinity to the 0 power is 1. That is kind of an interesting result.